So again, these are the steps to take decisions that we already mentioned last week, and these are the steps. And then if we talk about strategies, then we have a couple of possible strategies usually, and they are water savings on one hand, and let me see if I can, okay, fine. Okay, let's do like this. And mobilizing more water and water savings. And as I said, water savings have the priority today, because mobilizing more water means to build structural infrastructures and to build dams, to get more water from the rivers, and these are all interventions that have a significant environmental impact, and therefore people today are more keen on considering the option of water saving, and water saving can be extremely an extremely useful strategy, because as I mentioned in the past lectures, we have a lot of water losses in our water distribution networks for both irrigation and civil use, and therefore water saving is indeed an interesting option. Now let's move forward and try to better understand how the decision is taken in practice, and we get into the technical problem now. So basically, we have identified several alternatives. I said that basically these alternatives can follow different strategies, and I also mentioned what is the preferred strategy, but at the end we have identified alternatives. So for instance, one alternative can be to build a dam, and the other alternative can be to renovate the infrastructures to reduce water losses. Now we have to take the decision technically, so how can we take the decision? And this is not a trivial question, because I already mentioned to you that the decision should be taken transparently by involving all the stakeholders, and therefore the method that we follow to identify the best decision is of paramount importance. It's very important, because you know, when you have to take a decision by involving a lot of people, it's strictly necessary that the decision is objective, not subjective. I can't decide by just saying, I know that it's better to build a dam. I need to prove that it's better to build a dam. And therefore, from the technical point of view, this is a very relevant question. So, practical methods for taking decisions are part of a discipline that is called decision theory. And decision theory is a discipline that is related to engineering, but traditionally is not considered part of engineering. And these methods for taking decisions are used by economists, are used by people working in urban planning, but we are not used in engineering to teach these methods, which can be considered as a part of a related discipline. They are not traditionally part of engineering, and I am aware of this. But today, these techniques for taking decisions are becoming more and more important, not only in water resources management, but in different branches of engineering. And therefore, this is why I decided to deal with these methods within this course, within this subject, because I think that it's useful for you to have an idea of how these methods work. And this is a discipline that is tremendously evolving. So it's not really easy to suggest a textbook, to suggest some informative material, because the discipline is evolving. And you know, it's also evolving because with the progressing availability of computer resources, the discipline changed a lot. Now, Let me put some basis, some definition. First of all, we need to quantify the decision numerically. We have to translate the decision in a number. Like in statistics, we associated a random event to a number, which is a random variable. Even in this case, we have to associate the decision to a number in order to be able to deal with the decision analytically. And the number is called the decision variable. And the simplest example of decision variable that we can make is, for instance, water allocation. Water allocation is usually measured with the units that are used for water flow, like liters per second. So basically, you have a measure of the available water, like 10 liters per second, and then you have 3 users to serve, and you define the allocation as the water flow to each user that you assign to each user. For instance, you may have user A, B, and C. They ask for water, and you may also set up that the available water flow that you have is Q, which is, for instance, 10 liters per second, and then you have to define XA, XB, and XC, which are your decision variables. And of course, you have a constraint here. And you have a constraint because I told you that if we added a constraint, then there wouldn't be any problem to solve. The constraint is, of course, that XA plus XB plus XC should be less or equal than Q. And therefore, you have to find the values for these decision variables. Your decision consists in assigning numbers to the 3 decision variables. And the vector of the decision variable, so the vector XA, XB, XC, is called the decision plan, and usually it's called with the letter capital P, but, or you may say capital X. Let's say capital X, which is more consistent with the fact that you define each individual decision variable with X, by using the letter X. So you read here, decision variables are subject to constraints, which must be identified, because there might be other constraints, like, for instance, there could be the case that B needs a minimal water allocation, otherwise the water that you give him is useless. Like, for instance, let's think that B asks for 20 liters per second of water because he wants to build an industry which needs 20 liters per second of water. So maybe that if you don't give 20 liters per second, which you don't have, and you give 8, like, maybe that he can reduce the production, or he can change the workflow in the industry to use less water. But it might be the case that if you don't give at least 5 liters per second, he's really not able to do anything, and therefore it's useless to give him less than 5 liters per second of water. So there could be the constraint that XB must be, for instance, greater or equal than 5 liters per second. And all these constraints must be identified. And of course, to identify these constraints means, first of all, that you have to quantify water resources availability. So you see that this problem comes downstream after the other problems that we talked about before, estimation of water resources availability, for instance. So once that we estimated water resources availability, if we needed to do that, then we can take our decision. Okay, so the question is how we decide. And you decide by using an aid, a tool that helps you, a decision model that helps you to take this decision. And these models are usually called decision support systems. So when when you listen people talking about a decision support system, DSS, it means a model that helps you to take this decision. And this model, this decision support system, shouldn't just help you to take the decision, should also help you to explain that your decision is reasonable to stakeholders. So it should be transparent and open, which means more or less the same thing. And you understand that if you write a code, a computer code, this doesn't really help you to explain to people why you took a decision. You can't just show to people a computer code that only you understand and say, I use this. So this is the reason why decision support systems, in order to be transparent, they usually don't consist, at least the external appearance, of just a computer code. But they consist of something that at least the user interface is clear and transparent. This is the reason why they often use object-oriented programming. Object-oriented programming is a way to set up a computer program which is alternative to the use of a language, a programming language. In an object-oriented system, you have your screen, and in your screen you identify a dam on a river, and you put here the value of the storage, for instance. Storage equal something. And you identify your water distribution network downstream. And then, if you have a limitation, for instance, the pipe cannot bring more than a given quantity of water, you can just write max Q equal asterisk. So everything is visible. So this is equivalent to writing an instruction, for instance, in Fortran code, which says dam capacity equal. But of course, the advantage of the object, you see a dam is an object, the pipe is an object. The advantage of object-oriented programming is that it's more transparent. People can see what you did. So you can tell people, look, I have a dam, the storage is, the maximum storage is like that. I have a series of pipes, and they can bring only a certain maximum amount of water. I have the requests downstream, and the requests, the demands are demand A, demand B, demand C are clearly listed. And then you better explain how it works, how the system works. There are many examples of object-oriented software, and you know, the object-oriented software, the main advantage is just the fact that it's more transparent. Usually they have some disadvantage, which is related to the speed of the model. They are usually slower because, you know, for obvious reasons. They have an interface which takes computer resources, and therefore they are very often slower. So, let's now get into the details of a decision support system. So what are the methods, the technical methods that can be used to identify the best decision? And I will introduce you a couple of examples. First of all, let me anticipate that I will not show you any example of the use of a decision support system, because they are a bit complicated, and you know, it takes some time to get into the model, the program. Even if it is clear and transparent, it gets some time. I can give you some examples if you want. You may look at a couple of softwares which are indeed very good examples, and the first is the EPANET software. EPA stands for Environmental Protection Agency of the United States, and NET means that the software is suited for modeling water distribution networks. And it's a good example of an object-oriented program. It's available for download, so it's free. You can download it. It's open source and publicly available. And it's extremely useful if you need to design water distribution networks. And typically they are networks made by, like water supply networks for civil use, because the pipes are pressure pipes. And I think you can introduce open flows in channels, but I'm not sure. It was designed for pipe networks, pressure pipe networks. I'm not sure if they incorporated now no, probably, because you have already some experience on this. Okay, that's fine. And there are also other examples of softwares for the simulation of canals, but they are not object-oriented. So this is object-oriented, and this is a good example. Okay. Now, I said that I'm not going to practically consider these softwares, but I want to present you some examples, starting from a very classical example and starting from analytical methods. Because when you have to identify a best decision, basically one option is to maximize an objective function, to optimize an objective function. And we already had some experience in optimizing, because you know that in R there are algorithms that allow you to optimize objective function. This is a usual way of taking decision. And there has been tremendous progresses in optimization in the last 20 years. But when computers were not available, the identification of the optimum, maximum or minimum of a function was done analytically by equating to zero the partial derivatives with respect to the decision variables. So this is the first example that I wanted to give to you. And in the past, the classical example, so first of all, let me say that the method is called method of Lagrange multipliers. Do you know it already? Yes. Or, yes? Okay, that's fine. So I'll be very quick. And basically, in the past, what was maximized was a net benefit function, which is indicated here with the symbol MB. Net benefit means, of course, the net benefit that you can take by allocating the water. And this is basically an optimization based on an economical paradigm. And today we tend to include in the decision more criteria. So today, just the net benefit of a project, of a water distribution project, is not a sufficient criteria to identify the best decision, because we are also concerned by environmental impact, we are concerned by issues that cannot be really well quantified by associating costs or benefits. Of course, one could translate the environmental impact in a cost function and then taking it into account when computing the net benefit, because one takes the gross benefit from allocating water, gross means low or low, and then if you subtract the costs, you get the net benefit. So in the computation of the net benefit, you could include other criteria that you want to take into account, like the environmental impact. But usually, today, there is a different philosophy. There is the feeling that the environmental impact is difficult to quantify economically. So people tend to assume, to take the decision based on several different criteria. One may be an economical criterion, and the other one can be the environmental impact quantified in a different way with respect to associating an economical cost. So, but let's see, by assuming that we can indeed identify a net benefit function, how we can identify the optimum of this benefit function. First of all, The decision plan is indicated by the letter capital X. So the net benefit depends on the decision plan, which is a vector that is composed by decision variables which are called xi. The usual example is to include 3 decision variables, x1, x2, x3. And if you put them together, you obtain the decision plan. So basically, the idea is to find the optimum of the net benefit by equating to 0 the derivatives with respect to the decision variable. But in the case you have some constraints, you can't do that. Because if you just equate to 0 the partial derivatives, you could get to a solution which doesn't meet the constraints. So you have to include some conditions in the process to be sure that you are respecting the constraints. The constraints are indicated here by a function g of the decision plan capital X, which is in general equal to b. And let me make an example. If your constraint is, for instance, x1 plus x2 plus x3 equal to q, which is an equality constraint, which is the most frequent constraint, because usually you want to use all the available water but not more. So it's better usually, not always, but in many cases it's better if you use an equality constraint, which leads you to a simpler problem. If you use an equality constraint, you get to a simpler problem. So if you look at this equality constraint, you see that indeed it can be expressed in the form g capital X equal to b. So what you see written there is indeed consistent with the most obvious constraint that you have in water resources management, which is you can't use more water than available. Good. So how can we include this constraint in the process? The idea is to write a function which is called the Lagrangian, which substitute the net benefit. The Lagrangian is depending on the net benefit and is substituting it. And so that we move to an optimization of the net benefit to an optimization of the Lagrangian. And what is the idea? The idea is to introduce in the benefit function a penalty if the constraint is not satisfied. You see here, the constraint is gx equal b. So basically, if I bring b to the right hand side, I could write the constraint as gx minus b equal to 0. And if it is not satisfied, it means, for instance, because I am allocating more water than available, it means that gx is greater than q. So gx minus q is greater than 0. This is an example of a constraint that is not met. So basically, gx minus q, gx minus b, is greater than 0, and therefore I'm introducing a penalty. Because you see, I penalize the benefit with this penalty through a multiplier lambda. Why a multiplier? Because, you know, I don't know how much relevant should be the penalty, how much the penalty should be. For sure, it should be proportional to the difference gx minus b, but I'm not sure if it is enough. So in order to make sure that the penalty is enough, I introduce a multiplier, which is to define, and I assume that the multiplier is a parameter, and therefore is an additional variable of my problem. At the beginning I had 3 decision variables, x1, x2, x2, x3, or which is the same xa, xb, xc. I introduced one additional variable, which is the multiplier. I just want to make sure that you understand the functioning of this multiplier. If the multiplier is too high, let me first of all discuss the case in which the multiplier is too low. And let me make an extreme example. If the multiplier is 0, I have no penalty. And so for sure I end up with a solution that is not meeting my constraint. So basically lambda cannot be too low, because the penalty should be enough in order to make sure that we don't end up with a solution that is not meeting the constraint. On the other hand, if you introduce a too high penalty, you may end up with a solution that doesn't allocate all the water. Because, you know, if the penalty, let's consider what happens if you don't allocate all the water, which means that gx minus b is negative. So the penalty becomes a price. And of course, if you introduce a price in the benefit function, if you don't allocate all the water, it could be that you end up with a solution which is not allocating all the water, and you don't want this. So you want a good compromise. You want that the penalty is high enough to lead you to use all the water, but not higher than enough. Not to lead you to use less water than available. Is it clear? And therefore this lambda is an additional variable that you need to estimate. And now we can move to the minimization of the Lagrangian. Now let me make an example. Here you have a slide that is full of equations, so don't look at the slide but look at the blackboard, which is better. And this is just a practical example. I don't want to develop it entirely. I just want to show that indeed the problem is not so complicated. First of all, we need, if you want to make an example, and I just would like to draw once again your attention on the fact that this is an analytical method. So the advantage here is that we are working analytically, which is not a big advantage today, because we have computers that allows us to go with trial and error. And definitely, with the current availability of computing resources, trial and error is definitely better. What does it mean, trial and error? It means that if you have 3 variables, x1, x2, x3, and their sum should be equal to 10, and you want to identify the highest benefit, why not to try all the possible combinations? This is very easy, by chance. You have 3 numbers, their sum must be 10, and you don't need to try all the numbers with a lot of digits. You may say that your required precision is just like 1 digit, and therefore you know that x1 is varying from 0 to 10. You have 100 possible values if you want to consider 1 digit. And then you have 100 possible values of x2, 100 possible values of x3, and then you could try by chance. You may ask to the computer to generate one number by chance, which is comprised between 1 and 10, x1, with 1 digit. And therefore, once that you generated the first one, x1, let's suppose that it's equal to 5.6, then you have 4.4 still available, SA still available. Therefore, you can asked the computer to generate x2 by chance in the range 0, 4.4, and let's say that the computer tells you 1.0, and then you have 3.4 still available, and then x3 is equal to 3.4. So you see, this is very simple. It's very simple to ask the computer to generate by chance a number between 0 and 10, and then in this way you can generate the second number in the range 0 remaining water, and then the third is computed by difference. And then if you do 1 million trials, you are quite sure that you are trying all the possible combinations. And there is no problem with the PC, and then once that you know the three numbers, you can compute the net benefit function because it's defined. It's part of your problem that you solved to compute the net benefit function. And therefore you can easily try 1 million, 2 million, 10 million times by generating by chance, and then you ask the computer just to remember the maximum benefit associated to a given solution. And after 1 million trials, which may take like 5 minutes, you have the best solution, which is very close to the really best one. So this is definitely the most convenient way of dealing with these problems today. And then it might be that you need to optimize the code, because this is very naive, and this code has a problem, doesn't remember the previous computation, doesn't learn from each computation. It just tries by chance, and he could try a solution that is very close to one that was already tried, and it doesn't learn from the trials. So basically people working in optimization devised softwares like the ones that we use in R, which remember the previous computation and learn. So they refine their research by learning. Okay, but for sure this is the best way to deal with these problems. But we are focusing now on an analytical method. What is the advantage? You get an exact solution, because strictly speaking, when you work with these softwares, you don't converge to the right solution. You converge to a solution that is very close to the right one, but it's not the right one. The right one is computed analytically. So the analytical method gives to you the correct solution, and it's very fast. It just requires a few computations. The fact that today you don't see any practical difference in making 3 computations rather than 1 million, you don't see the practical difference, because 3 computations may require to you more time analytically than performing 1 million of attempts. But this fact doesn't justify ignoring analytical methods. So let's focus on the fact that they are useful, in any case for your personal knowledge, and let's remember that we are working now in this context, analytical methods. Okay, I said that part of your problem is defining your benefit function, and let's assume now that we deal with the benefit function, which is considered a significant example in water resources management, which is given there. So let's say that the total benefit, if we have 3 decision variables, is given by the summation from I equal to 1 to 3 of a parameter AA, which multiplies 1 minus exponential, so e to the power of minus bi, second parameter, xi, allocation. This is my net benefit function, which is given here. What is the shape of this function? Let's visualize it for just one decision variable, like x1, for instance, because you see that this total benefit function is given by the summation of 3 individual benefits, which have the same shape, but possibly different parameters. So let's concentrate on one individual benefit. So this would be MB x1, And this function starts from the origin and for increasing allocation converges to A1. And the speed of the convergence is regulated by B, the parameter B. And this is, as I said, is a meaningful example in water resources management because, let me check if the camera takes all the blackboard until the corner, otherwise, yes. The camera is not really taking the video here, you can see the details in the video, but still I am concerned to stay within the screen. Okay, let me go back. I said that this is a meaningful example because indeed in water resources management, it might be the case that you start from the origin. If you don't give water to people, you have zero benefit, but then you converge to a maximum benefit because once that you satisfy people needs, then if you give more water, they don't get additional benefit from it. So this is a meaningful example, and this is also a nice, very nice function because it can be easily derived. I mean, not derived. You can easily compute the derivatives. Okay, good. So let's suppose now that we have this constraint, equality constraint, the sum of the allocation cannot exceed Q. Good. And also let's put an additional constraint, which is trivial. The allocation should be greater than 0. Otherwise, we could risk to get allocations lower than 0. And this is a trivial constraint that from a practical point of view we can ignore. And then our Lagrangian, let me write it here, is given by Lx